Welcome to this lecture where we will look a little bit more in detail on the effects that interference has on the propagation of light. So there's a particular phenomenon that's called diffraction, and we will try to describe this by the Huygens-Fresnel Principle. We will look at Fraunhofer Diffraction, and with that we can understand better what resolution optical instruments can have. And finally, we finish with Abbe's theory of the microscope in this lecture. So, first of all, if you have a light source and you have some aperture, you would expect the following thing. You would expect a spot like this, which is where all the light rays from the light source can go through the aperture, and you would expect a half shadow area where the light rays in this direction go through, so it will be darker like this. So this is the typical effects like you, for example, see in a moon eclipse. So then first the moon gets darker, and eventually it can get really dark when it's in the full shadow. So these are the same things. So there's a semi-shadow and a full shadow. In the same way, you can have semi-light and full light with a transparent aperture, as it is shown here. So this would be purely geometrical optics that would explain all of it. But interestingly, this doesn't work like this anymore for very small apertures. And if we go to very small apertures, you have to start to approximate light by the wave nature. You have to account for the wave nature, and you have to approximate it, for example, by these Huygens-Fresnel wavelets. So the trick is that you can imagine that this aperture space here, there's a wave coming in, and in the place where the aperture is, you can put lots of little emitters that emit a secondary wave, monochromatic secondary waves here, and when you superimpose these waves, it reconstructs the plane wave here, but in addition to it, it also gives you these curves a bit that show you the effect of diffraction. And so this is the theory we will be using. So we will look at this a little bit more in detail, back to what we looked at what we used at the very beginning of this lecture by emulating waves with water waves. So look what happens there. Now we've added, instead of two sources, several sources in a row at equidistant spacings. So you see here now that we have all these several sources. And then if you look at what happens in the waves, you see that at the beginning we still see these individual sources, but after a short distance they seem to melt together, and we have actually generated a plane wave. But of course, so this demonstrates Huygens' principle that you can synthesize a wave by superimposing lots of elementary waves. If we go to the limit, and I'm now taking out this little baffle so that we have infinitely many waves that are overlaid, and now you see nicely how you get an almost perfect plane wave that travels to the right. Maybe you ask yourself whether this wave nature is just something that concerns light, but of course that's not true. It concerns all electromagnetic wave, and even more than that, even everything. Because even electrons that you might think of particles also have a wave nature, so something that Louis de Broglie sort of highlighted, and you see here an image where you can clearly see the diffraction patterns that were obtained by imaging this carbon grid with an electron microscope. So we continue with another experiment, which is a very interesting story, as you will see. When you illuminate a pin by a laser beam, you will suddenly discover a bright spot in the middle of the shadow area of that pin. So there was this debate between Newton and Huygens' theory, the corpuscular theory of light or the wave theory of light, and eventually Poisson made a prediction that there should be, you should be expecting a bright spot in the middle of a shadow region when you analyze the diffraction from a circular disk. And so everybody thought this would be completely nonsense and impossible until Arago actually showed that this is really what you get. And this is what this experiment is going to show you. And you see here that we have a laser and a beam expander, essentially, that with a little pinhole that generates very good quality coherent light. And then here we have the most important bit, which is a little round object. It is actually just a pin with a nice circular head. And now we're looking at the diffraction pattern of this pin. Well, you see here it projects to here, and you see a nice round shadow. But in a second, we're going to take a very, very close look. So we first make it a little bit darker in the room, and then we take a close look now with the camera, and indeed you see Arago's spot here right in the middle. You see a bright spot in the middle of a shadow region, and of course you see some fringes, and this can nicely be explained, all of this, with the wave theory of light. The closer we look, the more we find out that actually diffraction and the wave nature of light is omnipresent. It's everywhere. You need it to explain the performance of optical imaging systems. You need it to explain the propagation of laser beams, the effect of diffraction gratings on the light, in this case even on seemingly non-coherent light or only a little bit coherent light. You can nicely see the colors are constructive and destructively interfering in such diffraction gratings, even for polychromatic light. For example, this, if you look at the CD, it shines nicely, and in fact some of the colors naturally occurring are explained by diffraction or interference effects. And of course you needed to explain effects such as holography or diffractive optics, which is becoming more and more common even in consumer components nowadays. So diffraction means waves propagate into the geometrically optical shadow zone. So it sort of opposes the field of geometrical optics, where you don't have that effect, but at the edges, sharp edges or features that are smaller than the wavelengths, then you have these non-rectilinear propagation where you need diffraction to explain it. And of course, the person who really first considered this seriously was Christian Huygens, who lived 1629 to 1695. And he said every point of a wavefront serves as a source for secondary spherical wavelets. So we've seen it in this graph before. That's called the Huygens principle, or the Fresnel-Huygens principle. So there's Auguste Fresnel. He looks like this. And he had this idea of the superposition principle, saying that explaining destructive and constructive interference. So it says that every point of a wavefront serves as a source for the spherical secondary wavelets, and the superposition of all these wavelets generates the new wavefront. So that's why it's called the Huygens-Fresnel principle. There's an interesting theorem that's called Babinet's theorem. So what does it state? It states that the diffraction pattern from a hole in an opaque body is equal to the diffraction pattern of an opaque disk of the same size and shape. So basically, if you take away the direct transmittance, so to say, then both of them show the same diffraction pattern. That might be quite surprising, but it's a very useful and interesting thing, Babinet's theorem, showing an analogy between this diffraction and this diffraction. Or a diffraction from a hole and a diffraction from a disk are really just the same. If we want to quantitatively compute the diffraction pattern, for example, from such an aperture, we could use what is called Kirchhoff's diffraction integral. So the trick is that we would just need to perform an integral over all the possible position here and then sum up what is called the phasors or the complex valued amplitudes for light that travels along these paths here. So you can compute the optical path difference and take e to the I and then the phase that corresponds to it and then sum them all up. And if you want, you can also include the 1 over r decay loss in energy that you would have for this pathings, basically. So this ends up in the Kirchhoff diffraction integral. So now let's look at what is called the Fraunhofer diffraction pattern. That means we look at the approximation of going very far away from our diffracting object. In the next 3 experiments, we are first looking at what happens when you close down a slit around a laser beam. Then we look at the diffraction pattern of a wire, and according to Babinet's principle, you will see the same effects there. And finally, we look at the 2-dimensional diffraction pattern obtained by diffraction from a pinhole.
If you remember that experiment with the pinhole camera, we saw this effect that when we close the pinhole, the image got sharper and sharper. But I already told you that this will not remain like this. If we had closed the pinhole further, which unfortunately we were not able to do, then you would have seen that the image becomes more blurry. And this effect is called diffraction. We're going to see this in this experiment here, which is simply a laser. That laser illuminates a slit that we can close with this screw here. And while we are closing the slit, we are observing the diffraction pattern, which is shown here on the screen and filmed by a camera. So we can now zoom in here, and you see on the top left, you see me closing the slit, and there you see the spot. So as I close the slit, you see first a little line appearing that then starts to get subdivided into fringes. And as I close the slit further and further, the fringes go outside. So this is an interesting reciprocal behavior. Smaller here. In the far field, you get larger structures in the diffraction pattern. So as I close it further, you see how they go outside before eventually the whole light vanishes when the slit is completely closed. When I open it again, you see the opposite effect. The slit gets wider, and the diffraction patterns get smaller and smaller until they are not visible at all anymore. So you see here no further structure. However, if you look closely, you see right now here some interesting structure, right? There's a star with 6 rays. So where does that come from? It only is there when we look with this camera, but the other camera doesn't show it. So it must have to do something with the camera. And indeed, it is probably caused by the internal aperture structure in that camera. So if you had looked even closer, you would have seen also a little dot-like pattern. And I think that might come from the CCD structure and diffraction effects of reflections that have to do with it. But I'm not really sure what is causing this dot-like diffraction pattern in this camera.
So normally light travels in straight lines. However, if we obstruct its path or close by putting slits and close them far enough, you get this interesting effect of a diffraction pattern of a slit, as you saw in the last experiment.
This experiment shows the opposite of diffraction from a single slit. It's the diffraction from an opaque wire. So here is the setup with a laser and a collimator, and then behind it you see now the opaque wire. So you can see here how the light is diffracted from it, and then of course the screen on this side here shows you what's going on. And here you see that you have in the dark regions some bright fringes, which is sort of in the shadow region, and that means that light can sort of bend around corners, which gave rise to this famous discussion, and we're going to see next in the experiment about Arago's spot. So that means a bright spot behind a dark shadow region that people thought would be impossible.
What happens if we have two-dimensional patterns and we want to analyze the diffraction of these patterns? So in the case that we have a square aperture, it turns out that we can actually use our knowledge about what happens in the case of a slit, because we can write such a pattern as a product of a slit along X with a slit along Y, and it turns out that the diffraction pattern becomes actually a convolution of the two, but it's also separable. That means we can write this as a product of the diffraction pattern of the X slit with the Y slit this way. For the case of a circular pinhole, it's a little bit more complicated because we cannot do this. So we need to go back to our Kirchhoff diffraction integral, and it turns actually out that to explain this, you need to look at the Fourier transformation of a disk in 2 dimensions, which turns out to be a Jing function. So that's a Bessel function divided by R. And so here you see how such a function looks like as intensity. Of course, we are the Fourier transform of this would give us the amplitude distribution, which actually goes positive and negative here, and this is the Jing square function, so the Bessel over R to the power of 2. And it looks like this, and this is called an Airy pattern. Please do not call this an Airy function, because an Airy function has a totally different meaning in statistics, and we do not want to get confused, so call it an Airy pattern. Or if you want to refer to the central maximum here, you can call this one an Airy disk. So here you see that corresponds to the Airy disk, and if we get a polychromatic diffraction of a pinhole, a circular pinhole, we will see colors as it is indicated here in a simulation, and this is an experimental observation of such a circular disk.
In this experiment, we show the diffraction of a circular aperture. How is this done? Well, again, we have our laser, but then here we have a series of circular pinhole. And now, as you see, this is a 0.2 millimeter pinhole that we are looking at. And of course, now we are looking at the diffraction pattern far away on the screen here. So for this, we have to make it dark. So now you see the diffraction pattern on the screen, and it is this pattern of circular rings, and this pattern is actually called an Airy pattern. And what we are observing is now when I switch the pinhole to a different size, for example here, which is now the 0.1 millimeter 100 micron pinhole, you see a wider pattern. And interestingly, this pattern I tend to call the Jing or Jing square pattern, which comes from the mathematical structure of this that you will learn later. But one other thing is you see this first dark ring, and the thing in the middle, or the spot in the middle, is called the Airy disk. Yeah? You should try to not call this pattern an Airy, well, you can call it an Airy pattern, but please do not call it an Airy function, because this is a different term in statistics and might lead to confusion. But this in the middle is called the Airy disk, and you can call this the Airy pattern, or better, the Jing square pattern in this case.
Let's compare what happens when we move from the diffraction pattern of a single slit to the diffraction at a double slit. So you will observe that this curve goes into the red curve now. Interestingly, you can actually write this as the product of 2 different functions, because the single slit, to go to a double slit, you need to convolve it with 2 delta peaks. It means that due to the convolution theorem Fourier space. So in the far field Fraunhofer diffraction, we will get a product of the two Fourier transforms. And so that means we have to multiply the diffraction at the single slit, which is this typical sinc behavior, with the two delta peaks Fourier transform, which is a sine behavior. And indeed, what you see is a sine multiplied with the single slit diffraction pattern. Of course, we would have to do that at the level of the amplitudes rather than the level of the intensity as it is shown here. And so, but it still means that the single slit diffraction pattern is something like the envelope to the double slit diffraction pattern. So now we will look at the double slit in an experiment.
So you may remember Young's double slit experiment that we showed with polychromatic or white light, but here we have a very similar setup now with coherent light, so that we illuminate with our laser a double slit or a single slit, as I will show in a second. You see here that there's a little mechanism that allows me to close one of the two lines, and so currently we just have a single slit here. But when I open this, then it will become a double slit. So this is a very nice demonstration also about how mathematically you can describe the diffraction pattern. So if you think about it, a single slit can be seen as a rectangle, and if we now look at the screen, you would actually see the diffraction pattern of a rectangle, which is, if in the amplitude world, is a sinc pattern. So what we see, of course, is the sinc square of it. And when I now change this slit here by opening it up, then you see a modification, and you see the same pattern has been now subdivided here. So in fact, it's a multiplication with a sine pattern. Why that? Well, we have now a double slit, and a double slit is a rectangular pattern twice. So you can see it as a rectangular pattern convolved with two delta peaks. So that means here we have a convolution of a rectangle with two delta peaks, and here we will have the multiplication. That's the convolution theorem, the multiplication of the sinc pattern with the sine pattern, because the Fourier transform of two delta slit becomes a sine pattern. And of course, what we observe is the absolute square of it in the end.
We've now nicely seen the difference between single slit and double slit diffraction patterns. And of course, that doesn't only hold for light, but you can do similar experiments with electrons as well if you want to. Here the principle is shown again, the single slit pattern, the double slit pattern, and if you want to describe the amplitude in the far field diffraction, i.e. Fraunhofer diffraction, you would need to multiply the single slit diffraction pattern with the sinusoid. So now you may ask yourself what happens when we extend this not only to two slits but more slits. For example, an infinite number of slits, then of course we get the diffraction from a grating. And to retrieve the diffraction from a grating, we can use the same argument in real space. It's a convolution with many delta functions. So single slit gets convolved with many delta functions of big spacings. That means in Fourier space we get a multiplication of the single slit pattern as shown here with the Fourier transform of many delta functions. So we have to replace the sinusoidal pattern inside here with more dot-like appearance, delta-like appearance here. And then we would retrieve the diffraction of a grating with finite slit width. So let's look at the grating with red laser illumination.
Here we have a diffraction experiment, this time with a grating. And you see here the laser illuminates a grating. And this grating, we have 50 lines per millimeter and 100 lines per millimeter. So currently we are at the 50 lines per millimeter, and we look at the diffraction pattern that you see here, which has relatively small distances, and you can see many diffraction orders. Now that I'm changing this to the 100 lines per millimeter, you see that the first diffraction orders of the 50 lines have vanished, and we now see the first diffraction orders of the 100 per millimeter, which is, of course, twice as far apart as the original one.
In this slide, you can see examples of two-dimensional structures on the left and two-dimensional diffraction patterns on the right-hand side. And of course, there's like a whole science behind of how these relate via the Fourier transformation. And you see some of these different structures also in solid-state physics about the different space groups and how their inverse unit cell looks like. So we will now look a little bit more in detail how to understand at which positions we expect diffraction orders of gratings. So what you can see here is a little animation that shows you how a plane wave on the left-hand side goes to a single pinhole, and then we get a circular wave on the right-hand side. So this is the equivalent of a single Huygens wavelet. So when we now have a diffraction grating, which is a periodic structure of such pinholes, we need to figure out how these different waves from these individual pinholes in a grating superimpose and give rise to a first diffraction order. And I'm going to show you this now in a simulation. So here we have the parallel wave heading a series of pinholes from which again these individual Huygens-Fresnel wavelets emerge. And you can see now, after some sort of area where they all overlap, you see that here three main diffraction orders arise. That is the central zero diffraction orders going straight through as if there was no grating. There will be constructive interference along the straight direction, but there's also constructive interference along a diagonal direction here, the plus first order and the minus first order in this direction. And you see here now that we can sort of construct a plane wavefront along this direction. And the trick is now that there's always a phase difference between one emitting spot, one hole here, and the neighboring hole of one wavelength. And so because there's a one wavelength phase difference, we also get a parallel wave emerging in this direction. Of course, there would be a zero phase difference along the zeroth order and a negative phase difference of 1 lambda or optical path difference of 1 lambda rather along this minus first order. So let's look at this mathematically. So here is the pinhole screen, and so that's where the grating is, and now we need to figure out the first order. So central order would be zeroth order if we connect the wavefront like this, but if we connect the wavefronts differently like this, we have the first order. And you see now that from one pinhole here to the next one, there's always a difference of exactly 1 lambda in optical path. So that we can then formalize and therefore get to the equation of how this is generated, which we'll be doing in a bit. But before we do so, have a look at this experiment where we compare with the same grating the diffraction of a red, green, and blue laser. And because, as we just found out, we need a one wavelength difference, that wavelength is different, and therefore we get different angles in which to appear. And because the blue has a shorter wavelength, you would expect a lower diffraction angle for this first order of diffraction. Let's look at this.
This experiment is on the color dependence of diffraction. So here we have a nice grating with a lot of rulings per millimeter, and here we have a laser which actually is a combination of three lasers. You see red, green, blue laser, and they are with mirrors put together in such a small distance that actually on the screen they overlap and you just see a white spot here. And now when we put in the grating, of course, the white spot will become a superposition of, well, will become diffraction orders at different distances. And important is to see that the blue one has the least deviation from the direct beam. So the first order is at a smaller distance for blue, then for green, then for red.
As you've just seen in the experiment, the diffraction orders that we get when we illuminate a grating with red light are further apart compared to blue light. So if you watch here, we go to blue light, you see they are now closer together. So you've seen this graph before. Now we want to actually calculate the angle under which to expect the first diffraction order. And as you've seen, it depends really on the wavelengths, because when we have a smaller wavelength, then there will be a smaller diffraction angle. So if we want to formalize that, we need to say, okay, we have a wavelength in a particular medium, so that would be lambda standing for the wavelength in vacuum divided by n, which makes up in total the wavelengths in that medium. So for example, air, but it could be underwater, the whole experiment, or something like this. And now we need to make an equation out of this. So we have to say that this distance here corresponds to lambda over n. So that would be d times sine alpha, because this angle alpha here appears here, but also between the grating and these lines connecting the phase fronts here. So the wave fronts. So therefore we have d times sine alpha is this distance, corresponds to the wavelength lambda over n. Of course, that is therefore wavelength dependent, and we would expect the blue first diffraction order more here and the red one further outside. So a grating can also be something like a CD. That is, of course, normally not really a regular grating. However, since the CD is written in these tracks, you basically get a periodicity along the radial direction in such a CD. And therefore, if you put white light on it, it works really a bit like a grating, and you can see the different colors. And it also tells you that they've written CDs with the structures that are on the order of a wavelength. If you try the same for a DVD, you will be hard-pressed to do this, because the DVDs are so small, the structures are so small that it's very hard to see the diffraction effects that nicely on DVDs. So yet another structure that is made by nature, you will be seeing in the next experiment, which is using a morpho butterfly. And interestingly, we will also look at the effect of the refractive index in combination to the wavelengths here. So the lambda over n effect, as you will see.
So here we have a nice blue butterfly. As you see, we are going to zoom in for you to show. So a nicely iridescent blue butterfly, and its color is based on a photonic crystal. So what I'm going to do now is I'm going to put some ethanol, a few drops of ethanol, onto the wings of the butterfly. So hop, and look what happens. The color immediately changes from a nice iridescent blue to some green. And as the ethanol spreads, you see this green color, and we are now going to watch how the ethanol evaporates and the green turns back onto blue bit by bit. You now see the last little bits of green vanishing while it evaporates, leaving the blue color behind like you saw it in the very beginning of this experiment. Okay.
As you have just seen in the experiment, there's a very clear dependence on the reflected color in this morpho butterfly depending on the immersion medium that its own photonic structures is currently in. So how can we explain that? Well, what you see here is a zoom in with an electron microscope of such a structure from a morpho butterfly, and you see that it has this sort of three-dimensional grating structure, almost like a Christmas tree, which reflects this blue light if in air. When we now immerse the whole thing in ethanol, like we did in the experiment, that means that this distance that normally has to roughly correspond to lambda half, because it goes back and forth in reflection this time. So the structure would be lambda half in blue light. So if you take, let's say, 410 nanometers or something like this, and then this distance here is on the order of 205 nanometers. But now when we go to green light, that would normally not work, because it would be 500 something divided by 2, so more like 250 or so. But when we put this in ethanol, then the refractive index changes the wavelengths of green to correspond to the 210 nanometer in that medium. And therefore we get now the reflection maximum shifted towards the green, and that's precisely what you saw in this experiment with the morpho butterfly. So we've now seen that the wave nature of light can explain phenomena like diffraction or the first diffraction order from a grating. But how about standard effects? A good theory needs to be also able to explain what we knew before. So how about effects such as geometrical optics or refraction? Can wave theory explain refraction? So if you recap, we had a ray at a certain angle going to a surface, and it then changed direction. So what is the reason for that? In the wave picture, we have that wavefront. And normally, if we didn't have such an interface, it would look like this. The wavefronts would go like this, and the ray therefore travels straight on. The energy flows in this direction. However, now we learned that we have to account for different wavelengths inside the material. So when we now have an interface, like such as water, we have to reduce the wavelengths to something like this. And now you see we have a problem. At the surface, there's an electric field, and this electric field has to be continuous, or in other words, the amplitude of the wave has to be continuous. More precisely, it's the tangential component has to be continuous here, and you see that here, for example, there's a very big difference of half a wavelength. So this you're basically on a maximum here, and you would be on a minimum straight away in the water, and that is not allowed. And so the only way that this is possible to continue the wave is by changing its direction. And I'm animating this here by rotating a little bit the wave in the water. So if we rotate it like this, you now see that we again get continuous across the surface, all the wavefronts agreeing everywhere here. So from this we can then calculate Snell's law simply by forcing the waves to be continuous across the surface. And now you understand why actually the wave is forced to go to emerge at a different angle when you go into this material, in this case water from air. So here you see a nice animation that I pulled off Wikipedia, and you see how the wave remains continuous across the surface but emerges at a different angle, in this case towards the normal, refracted towards the normal. So how about waves that undergo total internal reflection? Normally we learned that they are perfectly reflected at this interface of water to air, or in this case glass to air, or perspex to air. However, if you do calculations with the wave nature of light, you find that there is actually a tiny little bit of field, electric field, in this so-called forbidden region. So you can think about this like the tunnel effect. Here the wave is not able to propagate, so free space propagation is not possible. However, you will find that there is an exponentially decaying wave that seems to travel along the surface. So if this wave was moving, this wave would look like it's traveling along the surface. And even though the wave is not really able to exist as a continuing wave, it can exist as a damped wave. And this is called the evanescent wave. So you can think of this being something like a bound wave. Now the cool thing is, if you have this bound wave, then you can put another surface close by, and if it's close enough, it doesn't need to be touching, then you can again couple this evanescent wave into a propagating wave, and therefore find a little bit of transmission. That depends then, of course, a lot on the thickness of that gap. And you can think about this in a quantum mechanical term as the tunnel effect. So the wave is tunneling from one side to the other side via the evanescent field. So of course, on top here you see ordinary diffraction with an angle that just about refraction with an angle that just about is possible, and here we're beyond the critical angle and only the evanescent wave can exist. So let's now look at resolution of optical instruments. So what is resolution? Well, if an object is very, very far away, for example, a double star, and we are looking at it with a lens, so we form an image of the collimated light in the focal plane, then we can call these resolved if we are able to see these two maxima. That is one way of defining resolution. And in this case, it would be an angular resolution. So that is typically specified in arc seconds or something like this in astronomy. So our optical system might have a resolution of, for example, 1 arc second. So here you have such an example of how an image of a single star could look like. And if we do the math, we find that we have 1.22 lambda over n as the resolution, as the distance between the maximum and the first minimum of such an array pattern that is formed as the image of collimated light, for example. So that would be a single star. If we now have a double star, we place them at this distance of 1.22 lambda over d, then you see something like this. And Sir Rayleigh looked at this and basically decided that this sort of placing one position, one star image, geometrical image, at the zero of the other one seemed to be roughly where we by eye can say they are just about resolved. If they're closer together, we call them not resolved. If they're further apart, we call them resolved. So this is the so-called Rayleigh distance or the Rayleigh limit of resolution. Since this image of double stars reminded me a little bit about something that I'm currently doing research on a little bit, I wanted to show this to you for a moment. So what you see on the left-hand side here is images of this double star. In this case, it's Epsilon Lyrae, and you see that each of them looks different. The reason is that there are atmospheric turbulences that are always there, and if your telescope is good enough, you actually see these very bad point spread functions. So the image of a star sometimes is better, sometimes is worse, but it's basically always distorted, but in a similar way for the two stars. And what you see now is that you can do smart algorithms that over time are able to figure out what are the real images of these two stars without the aberrations, and also what are the aberration maps So you see down here, for example, if you just summed all these images, that is what you do typically when you integrate long enough, then you just see very fluffy images and your resolution isn't that great. However, if you do this fancy reconstruction technique called iterative blind deconvolution, then you actually see the very sharp images of the two stars, and at the same time you get all the information about the aberrations that took place, and you see iteratively how the image gets better and better and better, and then it starts again from the beginning. So finally, for the lecture of today, we want to look at Abbe's imaging theory of the microscope. So Ernst Abbe had this smart insight of how to describe resolution in slightly different terms than Sir Rayleigh did. And what he said is he looked at structures that are periodic, for example, diatoms. So in his case, he collected diatoms which grow in little creeks, and then you can actually crush them, and you can take a little chip from one of these diatoms, and it is a very periodic grating structure, and it is very, very small, so that it's very hard to resolve this structure. And when he played with this, he sort of found out an interesting thing, which is, of course, if you illuminate that head-on with collimated parallel light, then you get the zero order, and because you want to now image it with an objective, you get sort of this effect, whereas so the zero order just focuses to the focal point, and the first order also focuses to the focal plane but in a different position. And then what he found out is that you get the image, so the magnified structure of that grating, you get that by the interference of the zeroth order with the first order, so like you see here. You can also have the minus first order. It also contributes to this interference and enhances the contrast a little bit. So if you now imagine we have the grating, it might look like this. If we only had the zeroth order going through the microscope and we block the first order, then we would not see the grating at all. All that was left was a constant gray value which stems from the zero order. So he saw that in his experiments. However, if you then allow one of the first orders to come through, so zeros and first order, they interfere with each other, and you get an image that looks like this, like in this case, like a sine square image. And so this allows us to resolve the grating. And Abbe now concluded that it's a good idea to call a resolution limit of an optical system that distance, here written as big lambda, the smallest distance where you're still able to resolve it, where you see any modulation of that original grating frequency. And now the point is that this really depends on whether the first order makes it through the optical system or not, and that's a very fundamental thing. And so in that sense, Abbe's limit of resolution is much more fundamental than most of the other limits, because it's a yes or no thing, and it cannot be tampered with so easily. So this is him, Ernst Abbe, and he said the basic structure of the object is resolved if the zeros and the first diffraction orders are both captured and brought forward to the image plane. So here's an example of if your aperture in the system, the back focal plane aperture, and you have to introduce one of those all the time, and in fact, even if you don't have it, ultimately there would be an angle of 90 degrees, and that would also limit your back focal plane aperture. So if you have, for example, the first order going through here for the blue light, you could just resolve in blue light this structure of the diatom. However, if you, for example, chose green or red light, you would see, oh, I can't resolve it anymore because they don't make it through the optical system, and then the resolution is gone. So you see that the resolution depends on the wavelength. However, Ernst Abbe then thought a little bit longer and found a way to overcome this. And the trick is that you send your light not orthogonal to your diatom, but you do oblique illumination. So if you illuminate from the button, the zeroth diffraction order would not be focusing at the center on the optical axis, but it would focus just at the side of the back focal plane aperture. And therefore, you can now go twice as large to the other side, in this case, even image the red with this oblique illumination. Yeah, and that doubles the resolution limit effectively in this trick. So please remember, Abbe's resolution equation is always about oblique illumination, or an illumination that at least includes these oblique beams. So now we are going to look a little bit more in details in several experiments on Abbe's theory of imaging.
So this is Abbe's famous diffraction experiment. What you see here is a model of a microscope. The microscope consists of a sample plane, of course. So here's our sample. We have then an objective that you find here. Here we have the pupil plane. Normally there's nothing there, but in this case we have a way to modify the pupil plane. So this way we can actually change what in the microscope, what information goes through the microscope and contributes to the image. And then here we have the tube lens. The tube lens will form an image on the screen over there. In addition to what a night microscope normally has, we have this little device here. And what it does, it takes some of the light, so a certain percentage is taken out of the beam, and then with this lens we form an image of the pupil plane right next to the other image. So that allows us to simultaneously see the image plane and the pupil plane. So what you see now on the screen is sort of a zoom into this pupil plane and the image plane here. On the top left, you can also see the modification device. So when I go with my fingers here, you see that I can now modify the pupil plane, and we can observe what happens to the image plane. So look at this. I'm closing the pupil plane aperture here, and you see that the image changes. For example, now we have only a few of these orders contributing to the image. Therefore, the image looks a lot blurrier. So let me go back. Here we have a relatively sharp image, and here we have a slightly blurrier image. When I then take away these orders, it is even more blurry. And when I finally have only the zero order transmitted, then all image information is gone. And I somehow imagine that this is maybe the, eureka moment when Abbe realized to form an image, you need interference of diffracted orders with the zero order. And what we're going to do now is we could do a couple of different modifications to analyze this concept a little bit further. So you see now what I put in here is a little device that you can see here that just lets pass one line of diffraction orders. In this case, we have no X diffraction orders, but we only have the Y diffraction orders, and only the central ones. So that means we have deleted all the X image information, and the blocks seem to be lines. Isn't that interesting that suddenly a two-dimensional object in the image becomes one-dimensional? You see fake information in some way, brightness where there was originally darkness in the sample. How is that possible? Well, because it's all about interference of diffraction orders. So this, of course, depends on when you rotate this. So, for example, if I go to a diagonal orientation, I get the interference along the diagonal, and you see a diagonal pattern. Even though the original block pattern that you saw there, the sample is actually just these transmitting square blocks. It doesn't seem to be in there, but of course, such a sample contains in its Fourier transform, if you want, also these diagonal orders. And if we just have them, all that is left is diagonal orientation. And if we go to the X direction, we can nicely now reconstruct only X information. So the next thing is I'm going to do the opposite. I'm blocking the central information here. Let me see to get that right. That's a bit better here. So we have no Y information left in the 0 order. So there's basically the 0x, the 0x orders have been blocked, and only the higher X orders are present. And what you see now is something interesting, that the blocks seem to be subdivided, and we have basically twice as many blocks as we had before along the X direction. And this is called a dark field imaging mode. We are seeing just the edges, and there's twice as many edges in the sample as there is blocks before. So finally, I'm going back to the original orientation. So you see here that we have again this nice aperture, which we can close and delete the information. And what Abbe asked then is how many orders do you need to see image information? So for example, the fundamental one seems to be this one. Here we lost all the information. Here we can see something, but we still have both sides. And is that needed, is the question. And it turns out it's not really needed. Let me show that to you, because I can now change the area that I let through. And you see, for example, now I've deleted that order. There's still some information visible. And I can also delete the other order by moving it slightly sideways. I thought I can. Okay, now. So you see that actually to get the fundamental mode of this two-dimensional grating, I only need interference of 3 different orders. And this led that Abbe to conclude that that the resolution really depends on what distance of the orders you can let through. And with that, he came up with the famous Abbe equation of resolution.
To now give you a little bit of a sneak preview on other microscopy modes, there's somebody called Fritz Zernike who got a Nobel Prize for an invention which is a nice method that helps you imaging a phase object. So the problem is with phase objects that normally, even though they do generate a first diffraction order and a 0 diffraction order and they overlap, the contrast in the image plane is extraordinarily small. Especially when you focus them very nicely, you get almost no contrast whatsoever. So in this case, Fritz Zernike found out that there is a phase shift between the zeros and the first diffraction order in the case of phase objects that is pretty much 90 degrees. The reason is that the phase object just makes a very small change in phase angle, but not in amplitude. And in a phasor plot, that means that the diffraction that gives rise to this change in phase angle is really just orthogonal to the original phasor. So that means a 90 degrees phase shift. And therefore, we have almost no contrast in the end. And so his trick is then to put a phase plate, for example, here in the zeros order, that also shifts by 90 degrees the zeros order. And if you do so, you get a much higher contrast. And you can combine it even with a slightly dimming here. So you dim down the beam, then the contrast gets higher even still, and you phase shift it by 90 degrees. And that allowed him to get much nicer images in the end, again by overlapping the zeros in the first order. So this is called Zernike phase contrast. So with that, we are done for the lecture of today, and we will continue with another lecture tomorrow.